we're set with the basics of the field and we're going to start solving some problems. And one of the things students notice very early about probability is that there aren't clear formulas that you can plug into. Yes, you have the two rules, plus and times. But there isn't one method. Every problem seems to require its own combination of those rules. Moreover, no matter which combination you decide to use, there are a few things that you have to be careful about. Precision in language. Terminology, notation, precision is really important, because if you confuse something like and with or, well, it's all over. So sloppiness of expression is hammered very hard and very early in probability theory. You need attention to detail. Don't leave out outcomes. Make sure you got everything. And above all, don't rush to an answer. Don't blurt a fraction. Take a moment to consider what you are doing. Yes, this doesn't sound good at all, does it? No student likes being told this. Be careful. Take it slowly. Nobody likes to hear this, but you know what? It is going to help. And since I know that this kind of thing gives students the heebie-jeebies, I'm going to try and make your lives a little easier by giving you some ways to organize your thoughts so that you can focus your ideas a bit more than just, what do I do here? And what I found in elementary probability theory is that it is a great idea to start out by counting the number of trials. Now, what's a trial? Well, I'm using that as a word that describes one stage of a random experiment. So, for example, if you are tossing a coin 3 times, you have 3 trials. Each of the tosses is a trial. If you are drawing cards from a box, then each draw is a trial. And so on. Each single stage I'm calling a trial. What's the smallest number of trials you can have? Yeah, 1 trial. Now, when you just have 1 trial, sometimes all these rules and edifice that has been developed is a bit of overkill. If you have just 1 trial and you know what all the possible outcomes are, you can do most problems just by counting. Let's take an example. So you've got a random number generator. Most of your computers have one. Sometimes phones have one. I know certainly there are many apps for this. A random number generator, what it's doing inherently is it's picking at random from the 10 digits 0 through 9. Each of them has the same chance, 1 in 10, of being picked. So the question that's being asked is find the chance that the digit that it picks, it's picking 1 digit, so it's running once, 1 trial, is what? Prime and greater than 5. Well, all right. They can ask us anything they want. That's fine. Now, the mistake here is to say, well, I've got an and, I'm going to use the multiplication rule. You're going to do nothing of the sort. This is 1 digit picked from these. What conditions must it satisfy? It must be greater than 5, which means it must be 6, 7, 8, or 9. Also, it must be prime. Well, of these 6, 7, 8, 9, which one's prime? Yep, the winner. Just the 7, and you're done. Only one outcome will work. That's 7. 1 digit out of 10 equally likely digits. Your answer is 1 in 10. Look, no rules. Well, there are rules in the background, but you don't have to do any formal application of a rule. So if you have the whole list of outcomes, just please stare at the outcomes and just count which ones satisfy the conditions. Now, sometimes the list is long enough that you don't have it all, you have it in a summary form. In that case, the rules do help. What really helps for me is the Venn diagrams, drawing pictures. So let's take an example there. I've got a class full of students and 15% of them have read Hamlet and 40% of them have read The Merchant of Venice. 5% have read both. I find that schools, at least here, assign The Merchant of Venice more frequently than they assign Hamlet. It's, I suppose, for young people in middle school and high school, an easier set of ideas to get their heads around. I'm not sure why. So what I'm going to do is I'm going to pick a student at random, a student, one trial. And the question I'm asking is, what is the chance that this student has read one of the plays but not the other? Exactly one, not 0, not 2. So what do? Well, if I had the list of all the students with the list of the plays that they had read, I would simply count, but I don't have that. So what I'm going to do is I'm going to list the ways that my event can happen, and what you're going to do is you're going to take out your paper and you're going to draw a Venn diagram. You're going to draw a blob of size about 15%. It doesn't matter, just draw a blob. This corresponds to the Hamlet people. Then draw a bigger blob corresponding to the Merchant of Venice people and make sure they overlap. That overlap has size 5%. So what is the chance that you are looking for? Well, if you think of chances as areas, you are looking for the area that's in Hamlet and not in the overlap, in Merchant of Venice, not in the overlap. And that is the partition that I'm going to do in words. The event A, they read Hamlet, but not The Merchant of Venice. Well, what proportion have done that? 15% of them have read Hamlet, 5% have read both, so it must be that 10% have read just Hamlet. Similarly, the percent that have read Merchant of Venice but not Hamlet is 40% minus 5%, and that's 35. So what you've got is this is the size of your Hamlet blob that doesn't include the overlap, and this is the size of your Merchant of Venice blob that doesn't include the overlap. And what do you want? Exactly, you want the total. And your answer is 45%. Now, if you want to be formal about this, you can say, all right, fine, the event that I'm looking at is the event A or B. The student has to fall into one of these categories. I don't care which, I'm happy with either. A and B are mutually exclusive. These people have read Hamlet, these people haven't, there is no overlap here. In fact, we have deliberately taken out the overlap. And so what is the chance of A or B? We've got an addition rule. It says add. And that's what we did. You don't have to go through that formal derivation in your head. But that physical sense of what is going on in the picture, or a logical sense of what is going on with the events, is the thing to try and develop. All right, so what have we done thus far? One trial. Well, all right, there's only so much you can do with one trial. Most events are going to have more than that. Next one up? Yep, 2 trials. And I'm going to take 2 trials with a relatively small number of outcomes, because for those situations, there is a wonderful method that allows you in one go to answer any probability question about those 2 trials. And that's the method of drawing a table of possible outcomes. Let's just do it in an example and it will become clear. So in my pocket I have a quarter. All right, all you non-Americans out there, these are coins. A quarter is 25 cents, a dime is 10 cents, a nickel is 5 cents. So I have a 25, 2 10s, and a 5. I'm going to pull out 2 coins at random in the way you stick your hands into your pocket and pull out a coin, and clearly that is without replacement. And the question I'm asking is, what is the chance that I pull out more than 15 cents? I'm going to stick my hands in and take 2 coins out. So what we're going to do is we are going to lay out the statement of the problem and its solutions in a table. And the table goes like this. The first coin that I get can be either quarter, the first dime, the second dime, or a nickel. And the second coin that I get can be one of those 4 coins also, so I will make a little grid. What this cell represents is the outcome. I got the nickel first, and then I got the quarter. This is a bad cell. It cannot happen. You're drawing without replacement. You cannot get the same coin twice. You cannot get the quarter twice. So this is impossible, as is getting the same dime twice, as is getting the nickel twice. So how many total possible outcomes are there? Well, this is a 4x4 grid, so there were 16 total, but I have taken away 4, and so how many do I have? I have 12. There are 12 possible outcomes of this experiment, all of which are equally likely. Alright, so what do I have to do now? I simply have to go outcome by outcome and see which ones give me more than 15 cents. Okay, well, anything that has a quarter in it is already 25, so it's going to give me more than 15 cents. And so all of these have check marks. Check mark corresponds to satisfies the condition more than 15 cents. Here, it happens to be 30 cents, 5 plus 25. So these are all more than 15. Here also there is a quarter. The second coin drawn was a quarter, so these are all check marks, more than 15. This one is I got dime 1 and then dime 2. That's 20 cents. That's more than 15, as is this. Anything else? I don't think so. This cell here, I have 5 plus 10. That is equal to 15. It is not more than 15. And so I believe we've covered the ground here. We have 12 equally likely cells and 8 check marks, and so our answer is 8 in 12. 2/3. We're done. And it doesn't matter what question you are asked about these 2 coins, you can simply figure out which cells correspond to that question's conditions, and then you count and divide by 12, and you're done. This is a very handy method. When does it apply? Well, it applies when you have 2 trials, because you have columns and rows. You have a table. More than 2 trials, you can't draw a table because you'll have to have an axis that's coming out of your paper. You have to have 2 trials, and then you have to be willing to draw the table. So I'm saying a modest number of outcomes. By that I mean a number that I am willing to write out in a table. I'm going to tell you, if I had 2 cards dealt from a standard deck, there is no way I would write out a 52 by 52 table, though some of my students have done this in the past, but I will not. I will want some better technique to handle that. But, you know, even 2 numbers drawn at random from 0 through 10, like 10 by 11 by 11 grid, maybe. Certainly, as your text does, 2 dice being rolled, a 6 by 6 grid is the way to go. So this is a wonderful method because it does not require you to think about, is this and, is this or, what am I doing here? Nothing. You just lay out all the outcomes. You are listing the ways in a table and then simply counting. So what next? More than 2 trials. Yeah. And that's where things get interesting. And I am going to look not just at more than 2 trials, but also at 2 trials which have so many outcomes that you are unwilling to draw the table. So with more than 2 trials, I can't draw a table because there are too many dimensions. And with 2 trials with lots of outcomes, I won't draw a table because I'm lazy. So in this situation, what do you do? And what you will find helpful, I hope, is to ask always the question, what does the first trial have to be? And it turns out that if you can answer that question cleanly, then the problem is usually rather straightforward to solve. And let's see what I mean by an example. So I'm looking at a die. It has 6 equally likely faces. If I just say die, you can assume that the 6 faces are equally likely. If I have an unbalanced die, I'll say so. And the faces show 1, 2, 3, 4, 5, or 6 spots. I'm going to take this die and I'm going to roll it 5 times. Right? So there's no way I can draw a table. I have 5 dimensions. I want the chance that none of the rolls shows a multiple of 3 spots. If I look at that, that sounds like a complicated statement. But we just take it one trial at a time. What does the first trial have to be? What's a trial? A trial is a roll here. What does the first roll have to show you? Well, it better not show you a multiple of 3 spots. So it better not show you 3 and it better not show you 6. So what can it show you? It has to show you 1, 2, 4, or 5 spots. You can say that very clearly. There's no other way. The minute you can say that, you know that the chance that your condition is satisfied on the first roll is 4 and 6. What about the second roll? What's that same die being rolled again? It's the same condition. So yeah, now you're in business. What are you going to do? Well, your second roll also has to show the same set. So does the third, and so on. So the first one, satisfying the condition, has chance 4 and 6. Now, of course, I want the second one to satisfy the condition as well, so it's going to be a fraction of that times what fraction? The second one has to satisfy the same condition. 4 and 6, and then times 4 and 6, then times 4 and 6, all 5. That's 4 6 to the power 5, and that's just over 13%. So what did we learn from this one? What we learned is we had 5 trials, so we need a bit more technique than writing out all possible outcomes. But we almost wrote out all possible outcomes. We just said it has to be this set every time. And then it's I want cake and I want ice cream and I want a holiday on a tropical island, etc., etc., etc. It's that. And you're done. So is there a situation where you won't be able to say what that first trial has to be? There is. But even those you can handle. So let's take a look at a drawer of socks, 10 of which are red and 10 are blue. I'm going to mix them all up and just pull out 2, which is kind of what happens when you're bleary-eyed in the morning and pulling out your socks. So I'll pull out 2 socks at random without replacement. I want the chance that I get a pair. What is the chance that they're of the same color? So let me play the game that I set up on the previous example, which is to ask myself, what does the first drawer have to be? Well, there are 20 socks in the drawer. What condition must the first one satisfy? Well, you know, there isn't a condition on it. There is no restriction on the first sock that I draw. 20 out of the 20 socks are fine to be drawn. And then what? Well, then the second one has to be the same color as the first one that I drew. And because there are the same number red and blue, no matter which color I drew the first time, of course the second time there are 19 socks left in the drawer, and there are only 9 of the color that I drew the first time. And that is quite helpful, because that allows me to say, the first card can be anything. I have 20 cards, I'll accept all 20 of them. So that first fraction is 20 out of 20, it's just 100%. I'll take 100% of the cards the first time around. No matter what I've got the first time, the second time I have 19 cards, of which 9 are of this color. And so overall, my probability is 1 times 9 in 19, that's 9 in 19, that's just under 50%. And so even though you couldn't say, well, the first sock has to be this color or that color, because of the balance in your drawer, you were able to just go ahead and solve the problem and finish it. And I know you're thinking, yeah, but what if it wasn't balanced? Well, that's the next thing we're going to do. So we have a different drawer of socks, and now we have 4 red and 16 blue. And we're going to do the same thing. We're going to draw 2 socks without replacement, and we want the chance that they're of the same color. So let's play the game that we played here. What does the first sock have to be? Could be anything. I'll take anything. So there is no restriction on the first sock, just as in the previous setting. So you can start out putting down a 20 out of 20. But now what? Well, now the second sock has to be of the same color as the first one. That is still the same. But the chances that you want to write down, that second fraction, depend on the color that was drawn first. And so now you don't know what to write down. And this is telling you that this method that we set up, but just trying to write down a string of fractions and multiplying, is not going to work as is. You have to look in a little more detail. There are different numbers of the 2 colors. So you actually have to list the ways again. Listing the ways is a great fallback option. And what are the ways? Well, I want a pair of the same color. So either I've got 2 reds or 2 blues. We can work with that. 2 reds, what's the chance of that? 4 and 20 times 3, 19. 2 blues, what's the chance of that? 16 and 20 times 15 and 19, that's the chance that the second one is blue, given that the first one was. So we can compute the chances of the 2 ways that this event can occur. We have partitioned the event into both red or both blue. And you have your 2 decimal answers. So now what is the chance that you want? Well, you're happy with either. So add up and you're done. So here is a situation where what does the first trial have to be did not have a sharp answer. And we found that we weren't able to deal with the second card. And so the answer wasn't simply a product of fractions. We had to do a little more work, look in more detail, decompose the event, partition the event, the 2 socks are the same color, into its component pieces, find the chance of each component piece, add up. And of course what we've done is we've partitioned it so that the 2 pieces have no overlap, so that this clean addition gives you the right answer. So does it get more complex than that? Can you always do this? Can you always partition? Well, you can in theory. In practice, though, you might not want to. And so last example. I have a deck of cards and I'm going to deal a poker hand. That's 5 cards dealt from a deck. And I want the chance that that hand contains at least 1 ace. So I remind you, the deck has 52 cards and there are 4 aces. So now I have to have at least 1 ace. Okay, what does the first card have to be? You know what? I've no clue, could be anything. Yeah, could be an ace, maybe not. Fine, then what does the second card have to be? Either. I still can't get any sharper than that. And what does the third card have to be? Well, still either. And I'm not really getting a handle on this calculation at all in this way. So that method is not doing well for me. So what else do I have at my disposal? Well, I can list the ways. List the ways of what? of getting at least one ace in 5 cards. So how could I do that? Well, I could get exactly one ace anywhere in the 5 cards. Or I could get 2 aces somewhere in the 5 cards and the other 3 are not. Or I could get 3 aces somewhere in the 5 cards and the other 2 are not. And you know what? I'm getting tired just saying it, let alone calculating it. I do not want to list all the ways. There are too many of them. So now what? Well, I could just fold my hands and go away. Or I could roll up my sleeves and list all the ways. Or I could pray that there is a simpler method. And you know, when your list of outcomes that you have to write down gets long, it's a great idea to think of the list of outcomes that you don't want to write down. The complement of your list. You've got a long list. Maybe what's left over is shorter. So what's the complement of at least one? If you didn't get at least one ace, how many aces did you get? You didn't get any. The complement of at least one is none. None, 0. Now that's a chance we ought to be able to find. That list is very short, no aces. Everything's a non-ace. So what we are going to do is we are going to calculate the chance of getting at least one ace as 1 minus the chance of the complement. 1 minus the chance of getting no aces at all. So now our job is to find the chance of getting no aces at all. So how do we do that? Well, this is an event to do with 5 trials, and I ask myself, what does the first trial have to be? Well, it has to be not an ace. Can I write down the chance of that? Oh yes, there are 4 aces in a deck of 52 cards. So the chance that my first card is not an ace is 48 in 52. Once I've got something that's not an ace the first time around, what must happen the next time? Also not an ace. And now what is the chance of that conditionally on the first? I think you have it. Yes, I think you have it. Not an ace, and not an ace, and not an ace, and not an ace, and not an ace. Here is your product of fractions. And that's something you can work out, and you have just over a third as your answer. And this is a classic method of finding the chance of at least one success in a set of trials. This occurs throughout probability over and over again in many different settings. And it is almost invariably done by looking at the complement, because the complement of at least one is 0, none. And that's usually a chance that you can write down. So I want you to take a moment and go back through these examples and see what you've been able to do with just a plus and a times. Very, very quickly, you've been able to solve quite involved problems just by varying combinations of those rules. Now, the only way to get good at these is to do them. So, have fun.